Hello everyone, I am Kausal Patel from Mechanical Engineering Department at Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. In this video, we are going to determine equation of motion and natural frequency of a simple pendulum and a compound pendulum. Okay, in simple pendulum, a mass is suspended with a pendulum as shown in figure. Here pendulum is weightless. Generally a string is used for that purpose. Okay, so to determine the equation of motion for simple pendulum and thereby to derive the equation of natural frequency and periodic time, we have to consider a simple pendulum having mass m, which is suspended with a pendulum having length L as shown in figure. Okay, so initially this would be the mean position. In this condition, the system is subjected to two forces. First one, that is due to mass, and it is weight W, and it is equal to mass into gravitational acceleration G. Okay, so in the opposite direction, the tension would be induced in string or pendulum, let it be T. Now initially this system is in static equilibrium, so that's why this both forces, tension T and weight mg, are in static equilibrium. It means both forces are having same line of action and same magnitude but in opposite sense. Okay, now let a system is displaced through theta angle from its mean position. So this would be the mean position of system, and system is deflected through the angular displacement theta. Okay, so that static equilibrium would be disturbed. Okay, here the system is moving in counterclockwise direction when viewed from the front. So it is having an acceleration in counterclockwise direction. So the inertia force I into theta double dot, that would be considered in the clockwise direction when viewed from front. Okay, now whenever at particular instant of time the system is displaced through theta angle, then the system is subjected to two forces. First one, that is weight mg in downward direction, and second one, that is tension in pendulum. Okay, but in this case these two forces are not in static equilibrium. So here we are going to consider two components of weight mg, and that is radial component and second one, that is tangential component. Here we already know that the system is displaced through the angle theta, so this angle would also be theta. So this radial component of weight mg, that would be mg cos theta, and tangential component, that would be mg sin theta. Okay, now in this case this radial component mg cos theta and tension in pendulum T, both are going to neutralize each other, as they have same line of action and they would have same magnitude but in opposite sense. Okay, so here limited angular oscillation, that would be due to this tangential component mg sin theta, and here due to this mg sin theta force, it would provide a torque having magnitude equal to mg sin theta into L in clockwise direction when viewed from the front. So here the system is subjected to two couple or moments, or we can say torque. First one, that is mg sin theta into L, and second one, that is inertia couple I theta double dot. Both torques are acting in clockwise direction when viewed from front. That we can clearly see from the FBD. Okay, now from FBD we can apply D'Alembert's principle, that is total summation of inertia couple plus all the external torque, that should be 0. So by applying D'Alembert's principle, the inertia torque plus external torque, that would be equal to 0. Now for small value of theta, sin theta could be approximately written as theta. So the equation is reduced to I into theta double dot plus mg theta into L is equal to 0. So that equation could be also written as theta double dot plus mg L theta divided by I is equal to 0. So that is our equation of motion for simple pendulum. Okay, now by comparing this equation of motion of simple pendulum with the equation of simple harmonic motion, we can get natural frequency omega n as in square root of mgl by I. Okay, so here we could get the natural frequency omega n is equal to in square root of mgl by I. Now for simple pendulum, it is assumed that the center of mass is located at the end of pendulum. So whole mass is concentrated at the end of pendulum, and that's why the mass moment of inertia of the system about the fulcrum point, that could be written as I is equal to m into L square. As we know that mass moment of inertia I is equal to mk square, but here in this case radius of gyration k would be equal to the length of pendulum. So mass moment of inertia about the fulcrum could be written as ml square. Now substituting this value in the expression of omega n, so the natural frequency in radian per second could be given as in square root of mgl by ml square. So ultimately omega n would be equal to in square root of g by L radian per second. So this is the natural frequency of simple pendulum. Now frequency in hertz, that is nothing but omega n divided by twice pi. So frequency in hertz fn could be given by 1 divided by twice pi in square root of g by L hertz. Okay, so here we have derived the equation of motion and we have get the expression of natural frequency by using D'Alembert's principle, that is one of the FBD method or equilibrium method. Now we can get the same equation of motion and same derivation using energy method, which is based on law of conservation of energy, and that is energy can neither be created nor be destroyed. It can only change its form from one form to another. Okay, it means total energy in the system would remain constant if there is no energy loss. So as we have discussed earlier, total energy U would be equal to kinetic energy plus potential energy, and that would remains constant. Okay, in simple pendulum, kinetic energy could be given by 1/2 I into theta dot square, that is nothing but 1/2 I omega square. Okay, so you don't have to confused with this equation of kinetic energy. For linear system, kinetic energy could be given by 1/2 mv square, but here the system is having angular deflection, so instead of mass we have inertia I, and instead of linear velocity v we have angular velocity omega, and omega that is nothing but theta dot, that is first order differential with respect to time of angular displacement. Okay, now here the pendulum is not fixed at the fulcrum point O, it is hinged, so it is free to have angular oscillation. So here in this case the stiffness of pendulum plays no role in the oscillations. So here there is no strain energy, but here potential energy, it is due to the gravity. So gravitational potential energy could be given by mg into h. Now as the system displaced from its mean position through theta angle, so this mass m, it also gains some height. Okay, so due to this elevation of height, the energy stored in the form of potential energy. So we can easily get the magnitude of potential energy by using this equation: mgh, m that is mass, g gravitational acceleration, and h that is elevated height. So we need to find out the expression of elevated height. This is not a dimensional parameter of the system, but we can find the value of h depending on the geometrical parameter of the system. So here we can easily see that the length of pendulum is L, capital L, and this distance that could be given as L cos theta, as the system is displaced through the angle theta, and this angle is theta, so this distance would be given by L cos theta. So now h, that is elevated height during the displacement of system through the angle theta, it could be given by capital L minus L cos theta. So ultimately h could be given as L minus L cos theta, so h could be given as L into 1 minus cos theta. Now substituting this value in the equation of potential energy mgh, so potential energy could be given as mgl into 1 minus cos theta. Okay, now we know that potential energy plus kinetic energy would remains constant, so it means 1/2 I theta dot square plus mgl into 1 minus cos theta is equal to constant. Now differentiating with respect to time, here in this term 1/2 I would remain constant. Okay, only we need to differentiate theta dot square, while in this term mgl is constant, here 1 is constant, but here cos theta that is variable, so we need to differentiate only cos theta, and the differentiation of constant term that would be 0. So by taking first order differential with respect to time, we can get du by dt is equal to 1/2 I, that is constant. Now differentiation of theta dot square, that would be equal to twice time theta dot into the differentiation of theta dot, that is theta double dot. So ultimately the differentiation of theta dot square, that would be equal to twice theta dot into theta double dot, plus mgl, that is constant, here differentiation of 1 it is constant, so that's why its differentiation would be 0, minus now differentiation of cos theta, that is minus sin theta, into the differentiation of theta, that is theta dot. So ultimately differentiation of cos theta, that would be equal to minus sin theta into theta dot. Okay, now for small value of theta we can consider sin theta approximately equal to theta. So finally we can get the relationship I into theta double dot plus mg L into theta is equal to 0. So this equation could also be written as theta double dot plus mg L into theta divided by I is equal to 0. So this is nothing but our equation of motion for simple pendulum, which we have previously derived using equilibrium method. Okay, now by comparing this equation with the equation of simple harmonic motion, we can get natural frequency omega n is equal to in square root of mgl by I. Now as we know that mass moment of inertia about the fulcrum point for simple pendulum, that is ml square. So by substituting this value we can get omega n is equal to in square root of g by L radian per second. Now frequency in hertz could be given by omega n divided by twice pi. So it is equal to 1 divided by twice pi into in square root of g by L hertz. Okay, you can also get periodic time tau p, that is nothing but the inverse function of frequency in hertz. So tau p could be written as 1 upon fn, that is nothing but twice pi in square root of L by g, and it is measured in second. So this is about a simple pendulum. Now next one, that is compound pendulum. So the procedure is the same, but first of all we need to understand what is the difference between simple pendulum and compound pendulum. So as we have discussed earlier, in simple pendulum a mass is suspended over a weightless pendulum. So it means the whole mass is concentrated at the end of pendulum and the center of mass is located at the end of pendulum in case of simple pendulum. So the mass moment of inertia I could be given by mass into length of pendulum square. But here in compound pendulum, mass is concentrated throughout its length of pendulum. Okay, here in compound pendulum the geometry of pendulum could be different, it could be irregular. So if the geometry of pendulum is known, then we can easily get the mass moment of inertia using the parallel axis theorem. But if geometry is complicated, then we have to find out radius of gyration and mass moment of inertia using experimental methods like compound pendulum method, bifilar suspension method and trifilar suspension method, depending on the geometry of an object. Now here, as we have discussed, in compound pendulum the mass is distributed throughout the length of pendulum. So let us consider a compound pendulum having mass m, and let its center of mass is located at the distance h from the fulcrum as shown in figure. So this would be the center of mass. So initially at this condition the system is in static equilibrium, so it is subjected to weight in downward direction and tension in upward direction. Both are going to neutralize each other. Now let us assume the radius of gyration of compound pendulum be k. So the mass moment of inertia of compound pendulum about the axis passing through its center of mass, that could be given by mk square, and let it be denoted by I suffix g. Okay, but here the motion is about the fulcrum point O, so that's why we need to find out mass moment of inertia about an axis passing through the fulcrum O. So that we can determine using parallel axis theorem. So as per parallel axis theorem, mass moment of inertia about the axis passing through the fulcrum of a compound pendulum could be given by I about O is equal to I about G plus mh square, where h, that is the distance from the center of mass and the fulcrum point. So the mass moment of inertia about the axis passing through the fulcrum could be given by mk square plus mh square. So finally it could be given by m into k square plus h square. Now let this system is deflected from its mean position. So initially this would be the mean position, and let it be deflected through an angle theta in counterclockwise direction as shown in free body diagram. So in this condition, the weight is acting at center of mass and it is acting in downward direction mg. Okay, tension would be acting in this direction, radial direction. Okay, so we need to consider two components, radial component and tangential component of mass. Let this be the radial component and this would be the tangential component. So as we have discussed earlier, this angle is theta, so the radial component would be mg cos theta and the tangential component would be mg sin theta. So here, due to the tangential component mg sin theta, the system is subjected to a torque mg sin theta into h, and it is acting in clockwise direction when viewed from front. Now as the system is having acceleration in counterclockwise direction, so the inertia couple, that would be in clockwise direction and it would be equal to I about O into theta double dot. Now from this free body diagram we can use Undamped principle, and that is nothing but summation of inertia couple plus external torques, that would be 0. So inertia couple, that is I about O into theta double dot plus external couple, that is mgh sin theta, that would be equal to 0. Now for small value of theta we can write down sin theta approximately equal to theta. So equation would gets reduced to I about O into theta double dot plus mgh into theta is equal to 0. Now let us substitute the value of mass moment of inertia about the axis passing through the fulcrum, and that is m into k square plus h square. So the equation would be reduced to this one. Okay, so by simplifying the equation we can get the equation of motion as theta double dot plus g into h divided by k square plus h square into theta is equal to 0. So this would be the equation of motion for compound pendulum. Now by comparing this equation with the equation of motion for simple harmonic motion, we can get omega n is equal to in square root of gh divided by k square plus h square radian per second. Okay, frequency in hertz could be given by omega n divided by twice pi, that would be equal to 1 upon twice pi in square root of g into h divided by k square plus h square. Okay, same way periodic time could be given by the reciprocal of frequency in hertz, that is equal to twice pi in square root of k square plus h square divided by g into h second. Okay, so this is about the compound pendulum.